So my name is Danny Lee. So today I'm going to talk about library characterization. And for those who don't know what it is, don't worry. I will go through the basics step by step. So first, a little bit about myself. My name is Danny Lee. I work for Empyrean Technology. I'm the R&D manager for characterization products, and I have 9 years of experience in library characterization. So today's talk will be presented by answering these questions. The first is, what is library characterization? Very basic introduction to library characterization, and specifically how to characterize memory and IP blocks. And then I'll go into what is variation characterization and why is it important for memory and IP blocks. And then I will talk about why it's difficult, what is the challenges, and what is our solution to this problem. And in the end, I will show some experimental results. So, it didn't appear before? So, okay. Now, the library characterization in short is to extract certain information from a cell design into a library, which is typically a file. And this file is being used in digital flows later. So it's normally for a given usage condition, we call PVT corners or some RC corners. It's one condition, and we run SPI simulation for that, which is the circuit device level simulation. And it's typically written in a specific format. And the most common one is called Liberty. Let's say we have a netlist X here for cell X. And after characterizing, after the process of library characterization, we get a library which contains the description of cell X, including these data, timing, power, noise, leakage, and so on. And among which the most important is timing. And also it is the most time-consuming to characterize. Right. And then this library is being used in digital flows like SDA or digital simulation. So what type of cell do we have to characterize? The most common one is, of course, standard cells. This is basic building block for digital circuits like NAND, NOR, the small gates, latches, flip-flops. But this is not what we're talking about today. We're focusing on larger cells like embedded memories and IP blocks. And the method that we use to characterize standard cells, like simulating the entire cell, doesn't work well for these big cells because these big cells can go up to a couple million transistors in size for one cell. So that is a very big challenge for simulating it multiple times to get all the data we need for the library. Okay, so how do we characterize memory IP block? Are there any optimization or smart way to do it? Yes. So there are two methodologies that solves this. One is dynamic and the other is static. The dynamic method, including simulating everything as a full macro. This is basically like the standard cell method, but it is slow, but it's doable. The simulation will eventually end and we get all the data, but just in a very, very long time. Also, we can do a path-based simulation, which means we cut out the critical path or the part of the circuit that affects the timing and do the simulation that way. Here's the diagram to show that to simulate the entire cell, the orange part is what we simulate. To simulate the delay from a certain input to certain output, we can simulate the entire block, or we simulate the relative part of the circuit. And we also have the static method. This is different because dynamic method relies on the top-level stimuli that we give to simulate the circuit. But static approach, we partition the circuit into even smaller blocks. It's like a gate-level partition. And then we simulate stage by stage. And this simulation is done automatically without user needing to provide any stimuli for that. So, and then we can add up the timing along the path to get the final result this way. And so this way, the simulation is much smaller, and we'll see the benefits later on. So a little bit more on how we partition in this static method. So today's talk will be focusing more towards this static method. So basically traverse the circuit through source and drain connection. This is one way to do it, but I know there are other ways, but this is the one we are proposing. So we stop at power and ground nets. So basically we get the full channel, all the devices that connected to the channel. And then this will be a partition. The partition includes only transistors, so RCs are already abstracted away. So only transistors, certain transistors are partitioned into one channel connected region. And this way we get this graph that's a little bit like a standard cell design. So we partition the bigger cell into smaller standard cell, but this is done automatically, and we can analyze the logic of each cell automatically and generate the stimuli to simulate each small block, small partition. So the benefit of doing this, first of all, is the simulation is much smaller, so we get very fast simulation, and we can use a higher accuracy simulator to do that. The second is since the partition is small, we can analyze the logic easily, and we generate the stimuli easily. So we can have more automation that way. So the result is we don't need user to provide the top level stimuli like the dynamic methods. And eventually we can use the SDA engine to find all timing paths. This is a well-solved problem. So that's the benefits. Now let's move on to another topic, which is variation characterization. So this is conceptually different from nominal simulation or the normal simulation that we talked about before, because in reality, there are randomness in process, from process variation. And what we get in the chip might not be the same as our simulation. And this is not avoidable. So we want to somehow capture this effect in our Liberty model, in our library. So basically, we're trying to answer a question, how much of value in library may vary considering process variation, right? And essentially, we're looking at each value that we characterize in library as a probability distribution instead of a single value. So here is a diagram for that. We have the same netlist. We can characterize it characterize the delay, let's say, into a table. So for different input and output condition, we can get a delay value. I'll just put some integers here. And this goes into the STA flow later. This is one library. But if we are doing variation characterization, what we get is a table of probability distributions. So this is basically saying instead of the delay being 1 or 1 nanosecond, it can be 1 nanosecond at a certain probability. It can be some other value at another probability. So it's a probability density function replacing each of the values in the table. And the way to use this data, of course, we can extract a certain margin out of this distribution and add it to the nominal values and then go back to the STA flow. Or this can be modeled in a separate way. So we basically describe this distribution somehow and use it in so-called statistical STA, which is more accurate considering the process variation. And this format is called Liberty variation format. There are two ways to model the distribution. One is sigma, basically we're capturing the worst case, and the other is moments. And we are capturing the shape of the distribution using some mathematical formula. So combining the two topics, why do big blocks or big cells, memory and IP blocks, need variation characterization? Why can't we just add some random margin, right? So it's because each path has unique variation. It's not a very uniform percentage that we can add. So we did a lot of experiments for that. And you can see from the left-hand side, there is a case, an SRAM case. We list all the arcs, timing arcs in the library. And you can see the variation percentage of these arcs vary a lot from arc to arc. The biggest one is data setup. I think it has 32% variation. And for delays, it basically within 5%. So if we want to add a certain margin, how are we going to not waste all these timing stacks? If we add too much, then the others are too conservative. If we add too small, then we risk some of them being, we don't get the required effect of variation characterization. On the right-hand side, we have the similar experiment on a DDR block. So you can see the y-axis is the percentage variation, and it varies a lot from point to point. Each point is a timing path. Now, we have spoken of why we're going to do it, but how? How are we going to characterize the variation for these blocks? So the most natural way is through Monte Carlo simulation. So it means, since we want to get a probability distribution, we just throw random samples and simulate them one by one. And once we have enough number, we can see the shape of the distribution, right? But this requires a lot of simulation. For bigger blocks, it can be very costly. I don't think it can be done for characterization, but sometimes it is done for validation purpose. That's okay. But conceptually, this is how it should be done, right? So we want, whatever method we have, we want to be as close to this as possible. And here, we take a delay arc, and we can see the distribution. We take the early and late 3 sigma points from 3,000 Monte Carlo samples, and we get 134 picosecond for early and 230 picosecond for late. So early and late means how much it shifts from the nominal delay. And you can see early and late are not symmetrical. We have a long tail at the right-hand side, which is late side. So we need to capture that as well. So the challenge for accurate variation modeling is we need a lot of Monte Carlo simulation for that. And also, if you say we can use smaller number, we can also capture the shape, but that's not the case, because here is an extreme example here. When we characterize when we get the sigma or some variation value this way, we get also a confidence interval because it comes from random samples. So the randomness will cause it to, we can predict it's likely here, but there's a range that it will lie in. So for example, we say 95% confidence level, it will lie in within this green box range. And the vertical line in the middle is the actual value we get, right? And so in this extreme example, when we use smaller number of samples, actually not very small, 5,000 samples, for this setup arc, we get a very big range in the confidence interval, which means this value we characterize is not that accurate, right? Once we increase number of samples, we eventually see the final, when we increase to 50,000 samples, the confidence interval is small enough, we can see the actual value actually is very different from the initial 5,000 sample case. So this shows us we need a lot of simulations to actually, sometimes for some cases, to converge on the final value, the accurate value. And as I said, for big designs, we're simulating, the bigger the simulation is, the smaller the number of simulation we can afford. So we want the simulation itself to be as small as possible to get the flexibility that we can simulate more and get the actual accurate value here. So how are we going to solve this problem? So in our product, LibreMem and IP, we do this by using the same partition that I showed before, the static characterization method. And we try to build a model for variation on these partitions, right? So for example, here is a timing path, and we have 4 channel connected partitions. And we'll build a multi-dimension function on each of these partitions. For each parameter of each transistor. So let's say for the first inverter, the delay, it's affected by 10 parameters. So we will build a 10 variable function for that to capture the delay change with the random parameters in the circuit. And this way we build these models for all the stages, all the channel connected regions. And then what we do is we can still use random samples, but instead of simulating the random samples using expensive simulation, we can just calculate using the model. So we get very fast Monte Carlo analysis without running the additional times of simulations and without running big simulations, because all these models are built at the CCC level, which means small simulations, right? And this way we can get 10,000, 100,000, even million samples very easily, very fast. And we still get the shape of the distribution that we want this way. So next I'm going to show you some experimental results of this method. The first is for memory, and the graph on the top is the accuracy comparison with Monte Carlo, 1,000 samples Monte Carlo, and we use our method for 100,000 samples. You can see the accuracy match pretty well, basically within 1% of Monte Carlo. And also, as I said, Monte Carlo with 1,000 samples might not be accurate enough. Right? The runtime benefit is huge compared to Monte Carlo. Here, I think it's 15 times the runtime difference, but note that our method, we were running full table, which means all the input-output conditions are considered, but with Monte Carlo, it's only one entry, so one input-output condition. That's also a multiplier. The peak memory usage also differs a lot. So here you can clearly see the benefit of using our method versus the traditional Monte Carlo method. And runtime is very important for this application. So comparing the runtime for nominal simulation, so this gives a more practical view. So in nominal simulation, let's say we use 1 hour, and typically the variation with the characterization with variation will take about twice that amount of time using our technology. So this is super fast compared to any other method that we know on the market So we can, with twice the characterization time, we can already get the full library with all the data in variation format. So and an example for IP block. So this is a DDR block with 2 million transistors in size. And we characterize the block in 2.5 hours, and variation included using only 5.5 hours. And the accuracy is really good within 1 picosecond of Monte Carlo. Right. This is real customer design. Another benefit of using this method by partitioning and modeling variation is that we can identify the design flaws or the design weakness caused by process variation. So we can analyze, because we have all the data stage by stage, we can analyze each stage and see for this timing path or this timing arc, what is the most biggest contributor for variation effect. And if the designer want to reduce the variation effect, then they can modify the design and fix that point. We can pinpoint to which transistor, which parameter. Here is an example. So we'll generate a report this way at the end of the run, and you can see we show the top contributors of variation in a sorted list. You can see which MOS or which and which parameter that this affects. We show the early and late sigma for this parameter alone, so it's an estimated value, so how big it contributes to the overall variation, and the weight and cumulative weight for that. So you can see the top 3 parameter already have 90% of the overall contribution. So we can focus on the top 3 and maybe change the design a little bit to make them less sensitive to variation. This can be a very, very useful tool for designers to adjust the design. Finally, I want to introduce the 2 software tools that we have for memory and IP characterization. So first is LibreMem. This is the advanced memory characterization system. It supports most embedded memory types like SRAM, ROM, CAM, etc. It requires minimal user interface input to generate the full library with advanced models like CCS noise, and of course LVF, which is the variation format. And we have LibreIP for IP blocks, and we support most common mixed signal or custom digital IP blocks like ADC, SerDes, PHY, USB controller, and so on. We have wide variety of methodology support for characterization, including the dynamic and the static method I mentioned before. And we have a hybrid method somewhere in between. So take the good part of the 2 worlds. And also includes ultra-fast variation characterization that I introduced in this talk. So that's the introduction to the software we have for this. So if you are interested or you have the need to characterize big blocks, so you're welcome to look for me later or in our booth on 2nd floor for more information. Thank you.